here. Did anyone have a chance to look at the quality of the videos from yesterday? The quality of the videos should be quite good. In fact, at least as good as Zoom. Uh, because that's actually being stored and recorded here off of my graphics card at my computer. So that's something that shouldn't have any variability whatsoever. All right, so again, we're here for digital signal processing, and I hope that you had the time to take the survey, uh, and also talk a little bit about the TA hours. So the video looks the same as your screen share. I'm not sure what that means. The one that you posted. Yeah, in fact, the video the video should look like what you're seeing, like my screen. It should be that's what's supposed to be recorded. Were you expecting something else? Did anyone have it? So was there an issue with the quality of the video?
No, not on my end.
Yeah, the posted recording should always be higher quality video than what you'll get in a live stream. And so, uh, we're talking about video quality, and it comes up. So when I posted that should be a high quality stream. So I'm just trying to understand the comments as they come in. So the posted recording will always be better, and it has to be better because it has a lot more bandwidth available in terms of writing the video to the disk right here. So with all of that being said, let's go ahead and proceed. Please keep me posted as we go about the status of the feed. I'd like to ensure that we get the highest quality possible. And so I kick off these lectures with the signal processing, start asking questions like, what is a signal? Can anyone volunteer me an example of the signal? Or any signal? We talked about, yesterday, we talked about one, which was EM radiation, electromagnetic radiation. We talked about a spatial frequency. You can represent a signal as a function. So so x of t is how we typically write signals in 3111, and then a discrete that's a continuous signal. And then x of n would be how we would denote a discrete signal. And so these are things that you were exposed to in digital signal process. I mean, in continuous signal processing, your 3111 class. But what are examples of actual signals? We talk about time domain signals. So EM radiation, that moves in time and space. So it sort of has a position and a specific location in time. So you can talk about the electric field at a specific point in space and at a specific time, and that's a signal. You can also talk about the acoustic energy or some kind of music signal. That's really a function of time. You could say that it's also in space if it's propagating through a room. But typically we think of it as a time function, or if we were to sample it, it would be an acoustic function of this variable n. So this is the x-axis variable. Time is typically denoted t, and this is called a sample index. And so, but I want to tell you that just about anything that we record is a signal. Well, anything that's recorded is a signal. Anything that you might record with some kind of, or write down, anything that you create and document is a signal. So whether it be a bunch of text, or whether it be an image or video, or the value of the thermostat, all of those things are examples of signals. Anything that we communicate is a signal. Everything that we actually, so a signal is basically any piece of information that moves around that we actually want to record and manipulate. So Signals are information-bearing functions, so sound, air pressure variation at a point is a function of time. There's a one-dimensional signal, so sound, a two-dimensional signal, a grayscale image, a three-dimensional signal, right? That's video, we talked about that. And then we can just go on and on with dimensions. And so I mentioned that in artificial intelligence, it's common to process, signals that consist of thousands, even millions of dimensions. And so there are sort of classes of signals. We have electrical signals as voltage, current, magnetic, electric fields, mechanical signals, velocity. You have inertial sensors like an accelerometer will measure accelerations, force, displacement, so forth. Acoustic signals, they have sound or vibrations, pressure, temperature, so many different kinds of signals. And so signal processing, we're going to be taking that signal and modifying it in order to extract, enhance, or rearrange the information in it. Anyone have an example of an information extraction problem? You get a signal and you want to extract information from it.
I just think of an audio filter of some sort.
Yeah, audio filter. Maybe you want to. So here's a cool problem in audio. You have a room full of people talking, and you have microphones in the room, and you can hear all those people talking, but you want to extract the voice of one person, say Johnny from the crowd, and provide on the output only Johnny's voice. That's a extraction problem. So here's another extraction problem. I saw a app on where you could play music. You could play some song that you might like. And after the first few notes, it'll take in the actual signal and figure out what the artist, the album, and the particular arrangement or the publication of the song, all of that information. Is that someone said something?
Oh yeah, so I was just gonna ask. So Shazam, the application is an extraction signal, where it just listens to just the music.
Yeah, it listens to the music. You basically turn it accesses your microphone and it listens to the music, and it's like, okay, I know that's this artist and on this album. Pretty cool. So yeah, RF, the get interference from similar frequencies being broadcast. There's lots of precise filters. So yeah, that's a very good point, Matthew. So in those cases where you're that's I think of that as sort of enhancement, but enhance and extract are a similar kind of problems depending on how you look at it. So in other cases, you have noise or things that perturb the signal, and you want to get rid of the noise but preserve the structure. For example, say that there's the example of RF signals. So say that you have a signal that's being transmitted in some radio frequency, but there's somebody else broadcasting, or maybe it's just ambient signals at that frequency. Well, they'll mix in with your signal, and then you have to try and remove them. And so in doing that, you're going to enhance your signal. And then so rearrange. Has anyone ever done Google Translate? That's a rearrange, right? You put in English, and out comes, I don't know, German. You're sort of rearranging the information so that it can be useful in a different form. That's how I pass Spanish. Very, very, very funny, worrisome. Let's see. So noise reduction is a case. Data compression, I always bring up data compression because guess what? It's just it's happening right now. And that's why things might look a little blurry and whatnot. But they're trying to take pictures and audio and send it across as quickly as possible. And then of course there's recognition and classification problems, or our signal processing problems. So in analog signal processing is an important aspect of things because we are analog beasts, and then the world itself is an analog world. And so most of the signals that we actually interact with actually have an analog source. They're continuous in time and amplitude. And then if we were to process these using analog methods, we would use analog components such as resistors, capacitors, inductors, and amplifiers. And so Humans are really, I don't know, I worry about saying the most advanced signal processors. We actually can process an immense amount of data. I don't know if I want to say advanced, because computers can do many things better than humans. They can see things better. They can detect subtle things that we could never see in images and stuff. But we're able to process all of this at a fantastic rate, given our different sensors and our brain, of course, which processes all of this information. So they do speech and pattern recognition, scene recognition, speech synthesis, all of this. And then examples of audio signal processing, well, there's communication applications like FM and AM and XM radio and things like that. And of course, video processing and traditional TV sets and, YouTube and all of the other contexts as well. So lots of different applications. And this is how that analog system works. We've got some kind of an input signal, and some kind of operator that operates on it. This is the system. So they call it signals and systems for a reason. This is the signal. This is the system. And often what you're trying to do is look at or understand the nature of the output. So the difference between analog signal processing and digital is just the nature of the signals that we're dealing with. So if we're going to process an analog signal, we take the analog signal as input, but we actually introduce some new things. This system here this is an analog system that would be here. We're going to do the equivalent. We're going to make this box here, we're going to make it behave like an analog system. All right, but inside of the box, we're going to have lots of digital components. So everything's going to happen in the digital domain. So this is an analog to digital converter. Analog to digital. And it's going to convert our signal P of t into a discrete function, P of n. Then here, the processor, this is going to be a CPU or some other processing, something that can do calculation. There are special DSP processors. There are central processing units, CPUs. There are GPUs, and actually I do a lot of GPU programming, graphical processing unit programming these days. That'll generate a discrete output, a Q of n, and then that will go through a digital to analog conversion. And once it's converted back into analog, it will be put back out into the 3D world. So for example, my voice, it's analog. The analog to digital converter, there's a microphone that changes that voice into a voltage. Then that voltage is converted into a number, a sequence of numbers. It's compressed by the processor and communicated over the internet to your computer. Your computer receives that compressed data, decompresses it, then it creates an output signal which represents the audio signal Q of n, and that audio signal then goes to a digital to analog converter, which is built inside your computer, and then your computer sends that to the loudspeaker that's on your wherever it is on your computer. And that actually takes my voice to you. So that's how it works for that particular circumstance. So let's talk a little bit about what happens here in this analog to digital conversion. All right, so we've got a continuous time signal, x of t, and we convert it into a discrete time signal, and this is x of n. And so the way that we do that is we take this continuous function and we take samples from it at specific intervals in time. All right. And so we adopt a notation. These samples, we give them indices. So n is an index for a sample. And so that's why the discrete function is a function of n. And the value of the sample, that's called the function value x of n. So x of n is the value of the sample, and the actual x-axis here is n. So this would be x of 0. X of 1 would be this value here, and this would be the value 0, 1, and so forth. So this is how discrete functions work, and this process is how a analog to digital converter functions. All right, so you have a discrete time signal as represented in the book is essentially a signal that has what's considered to be infinite resolution, right? And so actual signals that we measure, signals that we capture with digital signal with analog to digital converters, have finite precision. For example, what is the most accurate number that you can think of in terms of writing a program? So we've all taken C++. What is the most accurate variable type in C++? Does anyone remember? So there's the different kinds of variables. Let's think about what variables we can declare. There's int. Do we have an answer somewhere?
Someone put uint64, but can you add long as well?
So uint64, that's a 64-bit integer, and so you could. These are all integer values, which are accurate if you want to represent integers. What if we want to represent non-integer values? I see Nicholas wrote down float. So float gives you is a 32-bit representation. I see someone said double. That's great. And so double is actually twice as it's a 64-bit float, so it's actually more accurate than a float. And it's typically what you think of as the most accurate representation. And so fixed point, so then you can get into what's called arbitrary precision arithmetic and just say, I'm going to use a huge string of binary numbers to represent a number with an arbitrary precision. Of course, that precision has to be bounded. But
that's not necessarily a container, that's an array. So
yeah, right. So the array, so if you have so much memory in your computer, the array is limited by the memory in the computer. So any representation that we come up with, no matter what representation we choose, we will have a finite precision by which we can represent the number. And so the more bits that we dedicate from the computer to representing a single number, the more precision we can give it. In general, and we'll talk about it later in the class, in general, the double precision is the most commonly used one for high precision. And this will give you about 15 digits of precision for representing a decimal number. In other words, you will have 15 digits there that are meaningful, and anything after that is just randomly determined by rounding off the actual approximation. So a digital signal can only take on a finite number of values in such a case, right? Because you only have a finite number of values you can represent. For example, if we represented the value of a digital signal with 1 bit, how many different values can it take? 2. Yeah, right. So in general, if we have n bits, how many different values can it take? 2 to the n, right? So for example, an 8-bit number takes on 256 different values, and typically we call them like if it's an unsigned number, it will be between 0 and 255. Those are 256 different values. So and so that we're talking about this new world that we go into where we have limits to the precision that we have, and we have to be constantly thinking about the limits of the precision when we actually build. This class is being currently recorded, so it will be recorded and uploaded after class. So digital signal processing is important because it provides flexibility using the same digital hardware for many different applications, right? So I think that became really patently obvious with the advent of the smartphone, which is a single device that can do lots and lots and lots and lots of different things. So here, one of the key capabilities that digital systems provide is flexibility. You can use the same hardware to solve lots of different problems by just changing maybe the connectivity of the input and the settings or the parameters of the internal parts. So say you can change the settings for your analog to digital converter, your digital to analog converter, and you can change the actual program that you're using on the CPU and do all sorts of cool different stuff. And so before, when you have analog electronics and you're trying to do signal processing with that, you would build a circuit. And so, well, there's lots of uncertainty. Circuits have all these, it's kind of set in stone once you place it on the board. There might be a few dip switches or other things that you can do to the actual hardware to change its behavior, but it's kind of set in stone, not flexible. Okay, so these are other applications. We've already talked about applications a fair amount, but there's bioinformatics, automotive, telecommunications, military, mechanical, weather forecasting, economic forecasting. Can you think of another one? Anyone have an interesting DSP application that they've been exposed to?
Can you show the ones you just mentioned? I don't want to just say the one you just.
Sure. Yeah. So these are the ones. So there's, digital image processing, Photoshop. I mean, I'll mention one that I think is neat in a second here. So video compression, which we're using right now. Speech processing, like Siri, Alexa. Oh. I have to worry. I think I just triggered mine. Wireless comm, GPS. Gene analysis, medical imaging, like finding cancer.
There's one I saw where they read the vibrations like inside of an aircraft in order to and they use like a microphone to like make sure that it stays stable.
I see. So they're using an acoustic signal to infer like the stability of the vehicle. So that sounds like an interesting application. And that's certainly a signal processing context for sure. Like laser computer mouse, for sure. You have to figure out, the laser's giving feedback about the motion of the mouse, and that turns into, translation of your mouse cursor on the screen. Absolutely.
What about face imaging?
Yeah, face imaging, face recognition. All of that is certainly applicable. One of my things I think is kind of interesting is like the chess engines. They have these computers that will automatically play chess, and so you make a move and they analyze your signal in order to figure out the best possible response, and then they actually have they can mimic different kinds of levels of difficulty, so they can because at this point, that's one thing that computers can certainly do better than people. They can play chess much better than people, and that's very interesting. So keyboards, yes. Object detection, yes. These are all the Windows Hello. Yeah, I mean, all of that stuff. These are all instances. So I talked about the blind source separation problem earlier, where you have a bunch of people talking in a room, and they're all mixed together. And so we have these different microphones, and we want to actually figure out how to separate their speech. That's another example, a neat example of signal processing. Image denoising. This is a kind of similar to this context where we talked about before with RF signals that are interfering with one another. There's noise in signals, and for example, like the signals that come back from Mars and like from long distances, they're perturbed with all sorts of noise, because there's interference in the communication band. And so you can actually, even if you have an image that looks almost unintelligible, with a 90% noise level, you can actually extract structure out of that like this. And so that's one of those things where we're enhancing the image by removing noise and preserving the hidden structure. And so this idea of being able to extract hidden structure from signals that are extremely noisy is the fundamental goal of signal processing. And so the communication devices that we typically use, like the cell phones and wireless transceivers that we use for Wi-Fi and things like that, Bluetooth, all of those things, they operate in this regime where there's an extremely large amount of noise, and actually communicating those signals at those extremely high rates really relies on very sophisticated and efficient signal processing to make all of that technology work for us. Here's an example of an image enhancement, where we have and there's artificial intelligence now that does a very good job of this, where you can get a low resolution input image and then convert it to a high resolution output image. There's sort of simulated rain on an image, and then that could be removed. In fact, there's something that I worked on in the past was you have UAVs flying over cloudy skies and then removing the clouds, which is sort of a very similar kind of problem, so that you have a better chance of tracking the location of the vehicle. So it's sort of like when you're traveling in a plane, you look out the window and you're like, oh, I think I see this lake that I recognize. So you can actually use the images formed from the vehicle to estimate the position and orientation of the vehicle itself. It's called image-aided guidance. It's another area I work with. I work with the Air Force on topics like that. So you can also measure the heart rate with a smartphone or a camera, or you can with a smart watch, such as the one I'm wearing right now. Those are all signal processing problems. Okay, so what are we going to learn? So we're going to talk about DSP. We're going to learn about kind of review discrete time signals and systems and extend our knowledge there. Then we're going to go into the Fourier domain, and we're going to look at the discrete time Fourier transform. This is in Chapter 2. And then we're going to talk about the time domain interpretation of things at the same time. So this is also a Chapter 2 topic. Digital filter design is sort of something that we talked about after doing sample theory. So there's the DTFT is Chapter 2 and Chapter 4. And then we talk about filter design, which is Chapter 5 and 6. And then we talk about the DFT, which is Chapter 8. And the Z transform, which is Chapter 3. And so this FIR and IIR filters, we'll talk about them in just a minute as to define what these FIR means and IIR. But they're sort of part of talking about the time domain. So we cover a little bit of the ideas of FIR and IIR in Chapter 2. And then we revisit that concept when we start designing filters, which is part of Chapters 5 and 6. So this is an idea of what we will actually discuss in the class. All right, so these are the topics and where the topics come from in the textbook. So we spend a lot of time in focusing on getting the fundamentals right. So that's a lot of time in Chapter 2. All right, so we talk about linear time invariant systems or LTI systems, and those are specific kinds of discrete systems. And then we go into the frequency domain in Chapter 2. And that all sort of prepares us for sample theory, which is the idea of what happens to a signal when you sample it. You're converting something that has an infinite number of values, it's continuous, into something that has a finite collection of values, which is the discrete sampling. And so all of that sampling and quantization concepts, this idea of sampling, is all part of Chapter 4. And then we go on for the filter ideas of Chapter 5 and Chapter 6. Go on to do some filter design with Chapter 7. Then we have the discrete Fourier transform as Chapter 8. And then the Z transform we kind of circle back to as Chapter 3. So that's what we'll be covering from the textbook. All right, so hopefully we've already had a chance to take the survey. So this is all the stuff that I wanted to talk about that's actually sort of the remainder of the Lecture 1 lecture. Is there any questions on that people have while I load up our first technical lecture?
Yeah, Dr. Willis, I had a couple of questions here. So in one of the examples, well, let me go to this one. So in the slide where you're talking about discrete time signal versus digital signal, I was just kind of wondering, so whenever we have a continuous signal, right, and we discretize it, we turn it into a digital signal, right?
That's right, yeah. Anytime we have a continuous time signal and we put it into something like an analog to digital converter, the purpose of that analog to digital converter is in fact to take that signal and convert it from its representation as a continuous signal to a representation that's a discrete signal. So that's the one thing that it does is it makes that conversion happen. And so that's sort of in that block diagram. That's exactly what's going on.
Right. So what would be the difference between a discrete time signal and a digital signal then?
So discrete time, when we talk about discrete time in the like theoretical sense, sometimes people differentiate between we have a discrete time function and it can have infinite precision from a theoretical perspective, and then we have a digital signal which is a result of what comes out of an analog to digital converter. And so one of them you might say that the function has infinite precision and the other one does not.
I see. So it's just basically on the bounds, I guess.
Yeah, it's sort of the boundary between theory and practice. Like you can talk of a discrete function that can take on the value, say pi, right? Perfectly, and then, but if we ever try and represent that number, well, we don't have a system that can actually hold the number pi explicitly in the computer, and so
Right.
That would be the discrete, the digital function, the digital values that come out, right? So so that's sort of the difference between the two. One is sort of like a mathematical thing, and the other is really the actual kind of function you will get out of an analog to digital converter.
Right. Okay, that makes sense. And the last question before we move on. So in the example question about the microphones, where we were trying to isolate the different sound signals, it was something in there that said a square setting. In a square setting, that you had to make that assumption that it was in a square setting. So I was wondering about the square setting.
Okay, let's have a look at that real quick to see what we're talking about.
It's on slide 27. Or in a square ordering, that's what it said.
Oh, okay. So this actually had. So this is the actual configuration of this. So there are these audio clips here, right? And I didn't play them, but the audio clips were for microphones that were 60 centimeters apart from each other in a square order, right? So the length of the sides of the square were 60 centimeters, right? So in other words, the microphones themselves for this particular experiment where they have these different microphones, that's the actual relative positions of all the microphones. That's what that means. And so the reason, and so by doing, and the way that it works is like this. So to some extent, you can actually localize or identify the location. And this is kind of an interesting discussion. I worked on this a little bit in graduate school. You can identify the location of a source acoustically if you have 3 microphones. If you have 4, you can do it better, like you have an additional measurement. But if you have 3 microphones that are not at the same place, and then you have a sound emitted, and I suppose it's ancient history, but at that time they cared about the location of a sniper, and so a gunshot would ring out, and if you have microphones, the time of arrival of the gunshot sound to the microphone will be different for every microphone. And you know that if you make the assumption that the loudest or the first reception of it, the first, not an echo, but the direct path, is a straight line, you know that the acoustic energy emanates out on a sphere. So that means that the distance, so since sound travels at 300 meters per second, you can, depending upon the relative change in the time of arrival to each of the 3 microphones, you can actually pinpoint the exact location from in 3-dimensional space from which the shot was taken, which is interesting and cool, and it has to do with figuring out the time delay between the arrival of the shot, in acoustic sound of the shot, to the 3 different microphones, and so therefore you can localize or find out the 3-dimensional position of something. And so if you can localize them, then you can track them. And if you can track them and localize them, then you have a very good way to track the signal that they emit. Because other people moving around will have different time delays, so you can actually subtract that coherent structure out. So that kind of tells you about one way to solve the blind source separation problem. And also tells you why the knowledge of the geometry of the microphones is important. Does that make sense?
Yeah, that makes sense. That makes sense. And I'm assuming that it has to do with Doppler's effect, right?
So Doppler comes into play when people move around. So the Doppler effect is a shift in frequency that occurs due to the relative velocities of two things. So if a person, so there is some Doppler, intonation and things like that, but if the actual person, like geometrically, if the person were moving towards one of the microphones, there would be a sort of a micro Doppler effect that, like, their voice would shift in frequency, is what happens if they're moving towards the microphone. And of course, if some other microphone were behind them, it would be the inverse of that. Their voice would drop, sort of in a very small amount. Does that make sense?
Yeah, that makes sense. Thank you, Dr. Willis.
Okay, so let's see. Let's jump into lecture 2. Is there any other questions before I go on? Okay, so lecture 2, elementary digital signals, and so we're going to go over the basics. We're going to have homework 1 assigned, and so it's going to be, usually the first homework is given for 10 days, and so that's what my plan is, depending upon how we proceed in lecture. If we're able to progress in lecture more quickly, then we'll go ahead for 1 week. So it's going to be 1 week to presume, but I will extend it if we can't get through the content of the course, of the material on the homework before the end of class on Tuesday. So let's see, we still have 30 minutes today, so I think we're going to actually be in a good shape here. So this is the discrete signals lecture. We're going to talk about these discrete signals, and specifically we're going to review sinusoids. So we discussed sinusoids a lot in 3111. Their importance remains here, and please keep your ears open, because discrete sinusoids have some interesting and unique differences from continuous sinusoids. So from the book, this is chapter 2, the first section, 2.1. If you're using Orphandus, which is a free PDF I referred to, it's chapter 1.3. We're going to kick things off with this idea. I'm going to basically specifically list things that DSP systems do that we find attractive. All right, I mentioned flexibility earlier in class, but now I'm going to say these things are things that we need to know, because these things are things that I might ask were I to give you a quiz or examination. DSP systems are wildly popular because they provide that flexibility. They can change their behavior based on just changing the programming of the DSP or how we sample stuff. Reproducibility, that's incredibly important. Everyone has a cell phone these days. If we were to make these cell phones out of completely analog components, these cell phones would have noticeably different behaviors, because every analog component is going to have, like when you buy a resistor, most resistors have a 5% tolerance. You don't get exactly the same resistance in every resistor. You don't get exactly the same capacitance out of every capacitor. Digital systems, everything is operating in saturation. It's a 0 or 1 binary. So, and those are very stable, constant values. Therefore, when we build a digital system and we build millions or billions of them, they are highly reproducible. In other words, the cell phone that you get and the cell phone that your friend gets, if it's the same model, they have the same behaviors. That's reproducibility, which is really important for mass production. Of course, there's size. So that one of the main motivations and largest developing factors was the space programs for actually building small components, and sort of pushed forward digital design. And so smaller devices, and they're getting smaller every single day. Reliability, again, capacitors and inductors sort of degrade over time, and that certainly transistors can fail over time, but they are more reliable in the sense that we can build them. We have more ways to make transistors robust to difficult environments and the rigors of time than we have for, say, making a dielectric, not melt when it gets hot, for example, and things like that. So there's reliability over time, and also their behaviors don't vary as much over time. So finally, we can guarantee accuracy. And so that is the contract of, say, the float representation or the double representation or the byte representation. It says, I'm going to represent this number, and it's going to be an integer, and I'm going to have 256 different values that I can use. So that means that you are going to have error because it's not a perfect representation, but the error will always be bounded. So you can guarantee the accuracy of your representation, which is critically important to building engineering systems over time. And so these are some of the real important reasons that DSP systems are out there. Any questions on this? Okay. So anytime that I just replaced this. Why are these? I just replaced this. Why did this not? I will try and upload it again. So this, for some reason, replace the existing file. I just overwrote it and it still has my notations on it from when I gave this lecture last time. I don't know why that's happening. So I'm going to try and replace it again because the next slide seems to have annotations all over it. And it shouldn't. I've replaced it. I've replaced it again. I'm going to save this and so anytime you talk about the reasons that you should use DSP, I also feel like there's an argument like, when do you not want to use DSP? And so there are contexts where it's not really appropriate to use DSP. And so let's make sure that this... What is going on? Do I have to actually... I'm going to delete this.
Maybe you're uploading an annotated file that you.
No, I just looked at it. I just looked at the separate file that I'm uploading.
Because the one on Canvas is clean for me at least, the one that you gave us, so that one's good.
Yeah, I just uploaded it yet again, and I'm gonna look at it here. Yeah, I had to actually delete it. I couldn't. Wasn't actually getting replaced. That's frustrating. Okay, so I'll know in the future to just go ahead and delete those files. All right. So motivations against using DSP. All right. So really the main context where you might not want to use, because anyways, in DSP, what you're going to end up replacing a system. So an analog system would consist of just an input, X of t, the analog system itself, whatever it is, like a circuit, and then an output. So say it was a thermostat, right? The system itself we often represent as H of t, and say that it's a thermostat, which is a really simple. So if this system here is a very simple system, maybe it's okay to just build the circuit, and maybe you don't need flexibility. Like a light switch, which they're actually making digital now. I mean, so you can do dimming and all sorts of additional function, but a light switch is a simple thing. I mean, maybe we don't need a DSP system for that, because ultimately to replace that, H of T will be sort of mimicked by, we'll have an analog to digital converter, we'll have a discrete systems here, H of N, and then we'll have a digital to analog converter. All right, and so, and what comes out of that is Y of T, and what goes into that would be X of T. But you see, we've got three different parts. We have the analog to digital converter, we've got a central processing unit, and we've got a digital to analog converter. So we've got to put all this sophistication in order to solve the problem. So when we're trying to solve a simple problem, so solving simple problems that don't require all of this stuff, all of the flexibility, reproducibility, may not need a digital solution. But as time goes on, I see more and more of what I thought was a simple problem being converted to digital anyways. So having said that, that's sort of the case against the DSP. All right, so let's look at more detail what we've got here with a digital system. Well, that's the magnetic wave theory. I just tried to move this thing. Okay, so this is kind of tells you about all of the different parts. X of T is the continuous signal. X of N is the discrete signal. We have the analog to digital converter here, referred to as an ADC. We have the digital processor here, and we have the digital to analog converter. So all of the signals are labeled. So the signals, the analog signals are here and here. Those are analog. The digital signals are here and here. Those are digital. And then the actual thing that controls them, there's a new parameter on this slide that we haven't previously discussed. And so that new parameter here is the sample period. This is new. All right, so that new parameter is T, and T has units seconds per sample. It determines the time interval between one sample and the next when we take samples from a signal. So in this case, we let, for T equal to 1, there is 1, so there's 1 second here between the first sample and the second sample. And again, there's 1 second here between the second and the third, and so forth and so on. So T is the sample period. It is the interval in time between samples. Okay, and the sample period is a design parameter. In other words, when the ADC and the DAC operate, they have to know the value of the sample period, because they're going to be taking these samples and they have to know how often to take them. All right, now the inverse of the sample period is called the sample rate. And the sample rate is 1 over Fs. So if T has units seconds per sample, Fs has units samples per sec. And so these are the fundamental things that we sort of use in terms of talking about discrete time systems. These are important terminology. So I have a sinusoid written up here. So this function here is sine of omega t. All right, now it's going to oscillate. Can we estimate what omega is here? So if we look at this sinusoid, let's assume that this sinusoid goes through one period in 10 seconds. So does anyone know what the value of omega would be if it achieves a total period in 10 seconds? So let's write out omega is equal to 2 pi f, right? Now omega has units radians per second, and f has units hertz or cycles per second. All right, and so this takes 10 seconds to go through one cycle. So in terms of cycles per second, how much of a cycle does it go through in 1 second if it takes 10 seconds to go through one cycle? Yeah, 1/10. So F is actually 1/10. And so, in fact, we know we can, from that, directly write down omega. Omega is 2 over 10 times pi. And what would be the, so if this, and from 3111, what would be the period of this signal?
10, right?
Yeah, the period, which we have to be careful because we also called the period t. So I'm going to say t of x of t, the period of x of t, it's equal to 10 seconds. All right, so this is kind of review of concepts, review of sinusoids, and a little bit of new notation about digital systems. Okay, so
Dr. Willis, quick question, Dr. Willis.
Yeah.
So whenever we're talking about the sample period, is that the same thing as the fundamental period of the signal?
the sample period is the fundamental period of the sampling process. The fundamental period, so let's talk about periodicity real quick. So let's go and review that really quick. So a function is periodic in the time domain if x of t is equal to x of t plus capital T for some value of capital T. All right. So if it's satisfied, then if this is satisfied for some capital T, then you call x of t is periodic. Now, the difference between and t is the period. So the difference between the period and the fundamental period if the fundamental period is the smallest t for which x of t is equal to x of t plus capital T, right? And so for the example that we had before, say we had sine of what was it, 2 over 10 pi, right, times t. So this has you can say that t is equal to 10. And if in that case, we would have sine of 2 over 10 pi t is equal to sine of 2 over 10 times pi, and then you do t plus 10, right? And then you find that when you multiply this in, you'll get 2 pi over 10 t plus 2 pi t. And of course, sine of 2 pi t is 0, right? So it's not going to change anything, right? So it's just jumping. Sorry, no, it's not t. It's 2 pi without the t. Right? You multiply this out. 2 pi over 10 times 10, you just get 2 pi, right? So you have the same thing. So you have sine of this is equal to sine of this. And basically, for any trigonometric function, say you have cosine of x, that's equal to cosine of x plus 2 pi. It's also equal to cosine of x plus k times 2 pi for any integer k. Like you can take any 2 pi constant, multiply it by any number, like 4 pi, 6 pi, 10 pi, negative 10 pi. You'll always get back the same number. All right. And so the point is, so the question was about the fundamental period. The point is that there are many valid values of the period. 10 is correct. I could also write t is equal to 20, right? If I wrote t equal to 20, it still satisfies this relationship. It's still correct. But it's not the smallest value of t that I could write down. Does that make sense?
Yeah, that makes sense. Thank you.
So it's the small. So this would be periodic with a period of 10. That's correct, or a period of 20, or a period having any multiple of 10. And it's kind of like, to give you a very basic example. Let me create a periodic signal. Hello, 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 hello. Right? I keep saying hello. It's periodic. It takes me about a second to say it. So that signal is periodic, and its fundamental period would be 1. But I could actually consider groups of 2 hellos, right? And say that I'm repeating the 2 hellos at an interval of 2. And it's also periodic with period 2. That's the idea here. Anyways, that's what I'm going to go on, if that's clear.
Yeah, that makes sense. Thank you.
Okay. So so on the input side, we have a sampler and a quantizer. That's what takes this continuous signal, converts it to a digital value, which is quantization. Like, we have to assign it a finite precision number. And then we have to give that number an index, which is a sample index n. And so in practice, we take these signals and we sample very, very closely together. In fact, I'm working on a radar application where we sample at gigahertz. And in fact, that's quite common. Like, all of the computers these days operate like 2.5, 3 gigahertz is very common for a CPU to operate. So they take in samples and process them at that rate. And so therefore, the gigahertz is a frequency. Say that we are operating at 1 gigahertz, right? That's 1 e to the 9 hertz, all right? And so they say that was the operating frequency, fs, of something. What would be the interval in time between samples? The sample period would be t is equal to 1 over fs, and that's 1 e to the minus 9 seconds per sample. And so that gives you an idea of how, that's nanoseconds. So you're taking a sample every nanosecond. Okay, so here's an example of an analog signal up here, and we sample it, in this case, every 1/8 of a millisecond, and so we generate a dense collection of values on in the digital domain, and we call that function x of n. Now note that t is the horizontal axis here, right, and that has units seconds, or in this case milliseconds. The horizontal axis for the digital signal, this is n, and n has integer units. This is integer. And so there are 256 samples that will go from 0 all the way to 255. And so essentially, when you're measuring the signal, you take the continuous time signal, x of t, and then you fix t. You substitute in for it. You say, t, you're going to take on discrete values. All right, we're going to let n index the different locations where we'll sample you, and let t be the spacing between the values. And then we're going to call that signal x of n. All right, and so when we write that down, we typically write x of t evaluated at these locations as x of nt. All right, so this is the continuous time signal x. These are analog locations in time. Say that t is 1/8 of a millisecond. When n is equal to 0, we get x of 0. When n is equal to 1, we get x of 1/8 of a millisecond, right? And that corresponds to when n is equal to 0 and when n is equal to 1 for the digital signal. So that's why we convert. See, the x-axis is being converted from something having unit seconds to something having units of a sample index. Okay. So as I just pointed out, when we sample a signal or a sinusoid, we're going to relate time to a discrete index n. All right, this relationship is known if we know the interval in time between samples. T is one way to specify that, or we also have Fs is equal to 1 over T, so we can specify it as either the sample rate or the sample period. They both tell us the interval in time between samples. If I give it to you as Fs, you have to take its inverse in order to get the spacing of the samples. And so these relations preserve units. N is a sample index, and time and the associated time is this. So let's think about the units of everything. So T has units seconds, right? That is the time variable. The sample period is how many seconds expire between one sample index and the next. So its units are seconds per sample. And N has units samples. So if you take something having unit samples and multiply it by something that has unit seconds over samples, then you'll get back something that has unit seconds. So all of the units are compatible here. So the reason that I mention that is if you forget the relationship between the discrete time and continuous time, you can just say you're saying that T is related to N, and you know that T has unit seconds and N has unit samples. And then if you say something goes here that multiplies N in order to give unit seconds, the only units it can have are seconds per sample. So it gives you a way to kind of remember what goes there. And if you ever have to remember the formula, you know that T has unit seconds per sample, you'll know that T is equal to NT. All right, so there's this kind of cross-check about preserving units. All right, so let's give an example of how the sampling process would work out. For example, yes, for sure, there's a question about Austin about having negative sample indices. Absolutely. Sample indices in general, and will go from minus infinity in our theory to minus 1, 0, 1, all the way out to positive infinity. So for a signal like a sinusoid that goes on forever in both directions, n will also go on forever in both directions. I write it in terms of positive values just to kind of help us kind of track how it changes as we go away from 0. But for sure, it includes both positive and negative values. All right, so now I've got a sinusoid, and the frequency of that sinusoid is 1 over 10. That sounds familiar, right? We already talked about this. This is the same sinusoid from the earlier slide. And if you wanted to, you could actually go to MATLAB online, and you could see the MATLAB that I used to generate this. So here's the actual MATLAB that generated that sequence of frequencies that I used on the slide. So this kind of gives you an example of what that MLX file does for us. So here we have n varying from 0 to 10, and we have essentially the values for t equal to 1. So when t is equal to 1, we have a sample at time n times t, right? So we have n equal to 0, t equal to 1, n times t is 0 here. And so we go on and we see various other values. Now the actual thing that we're plotting here is the value of x at that time, right? So x at 0 is sine, so this value right here, this is sine of 0. That is the value of x of n. This value right here, 0.6, this is the sine of nt. In this case, n is 1 times t is 1, times the actual function itself, which is so this here, times 2 times pi times 1 over 10. And so if we punch all that in, which we can just jump over to MATLAB, so it's actually sine of 2 pi over 10, and we click on the command window, and it's 2, there we go, and we type in sine of 2 times pi over 10, and we press enter, we get 0.5878. I just abbreviated that as 0.6 in my slide. So, and that gives us our value here, 0.6. So if I wanted to sample for t equal to 1, I'm going to write a quick MATLAB code that does that. And we'll try and finish this slide before we actually adjourn class. But we have n. It's going to go from 0 to 10. All right, that gives me a vector of numbers, 1 through 10. If in MATLAB, I'm going to index the first value, n of 1 is 0, and n of 10 is its last value. And actually 11, it starts at 1, so it's 10. And I want to actually create a signal from this. So I'm going to say sine of 2 times, so I'll set a value for t. Our t is equal to 1. Okay. So now I have a value of n, which is a sequence of numbers, and a value for t, which is 1. So now I'm going to write down the function. I'm going to sample sine 2 times pi times the frequency, 1 over 10, times n times t. Press enter, and I just sampled that signal. You can see at index 1 I have 0.6, at index 2 is 0.95, and so forth. And so that MATLAB code I just typed in gives us this sequence of values that we have written down here. All right, and so that can give you, that should tell you how this sequence of numbers was generated. It's generated by actually sampling that. And if we were to plot that, these are the values: 0, 0.6, 0.9, 0.9, 0.6, 0, minus 0.6, minus 0.9, minus 0.9, minus 0.6, 0. Now, if we change t, in this case to 1/2, we're going to get samples at different locations. In this case, we're going to only sample the upper part here, because now we're sampling twice as often. We're only sampling every half second. We're going to take a sample instead of every second. When we sample more often, we're going to have our sample index increase faster, and we're going to sample more densely. So we're going to get 10 samples now over this region, because we're sampling at twice the rate. We're only letting 1/2 of a second go before we take another sample, which is why we get this signal here, which is just a more dense sampling. So I'll do that sampling in MATLAB, and then we'll have time for questions and adjourn. So now I'm going to let t be the value 1/2. So I'm going to change t to be 0.5. Then I'm going to basically run the same equation here. Sine 2 pi times 1 over 10, the frequency, times n. N is a variable that goes from 0 to 10, times t, which is now 1/2. And so now we got a new sequence of values. If I were to do a stem of the answer values, we'll see those values plotted. All right, and so with that, I think I'm going to, let's see, I'm going to collapse the command window so we can see that, and that's the stem plot, and it shows you those values. Those values are the same values that we see on the slide here. Of course, the actual slide, the plot is stretched farther in the x direction, but these are the same values here. So with this slide, we're going to sort of wrap things up. It's a little bit past the 2:15, and we'll pick up from here on Tuesday of next week. If you have any questions, stay after class, and you're welcome to ask those questions. So for those that are all set, you can leave, and you can hope you have a good weekend, and we'll see you on Tuesday of next week.
Thank you, Professor.
Thank you.
Professor, I've got a question. Do you have the textbook handy? Because it's from the textbook. If not, I sent you an email with the problem. You could look at it.
Right. I think so. All right. So Cheng didn't get a chance to get back with you on that, and I haven't either. Okay. So that was the moving average filter. So
Yeah.
So the moving.
It was the accumulator of a time invariant system, I believe.
Okay. So an accumulator is gonna accumulation is a lot like integration. All right. We're accumulating stuff, right? And so let's go ahead and so and write that out. So do you want to, was your question about the actual form of the summation?
It was just one step of it.
Okay.
So the top summation, so on top of the summation symbol, it goes from n to n minus n naught. I wasn't sure why. I got every other part of the problem, but just that specific part. Not sure why I shifted the top summation variable, or how, or what substitution was made.
Okay, and so
Yeah, it's steps that should I?
here,
Like,
give me a second to pull it up from my email, and then I'll just write it down because I'm sure that it's exactly in the email. Okay, so so we have the integrator system, and the integrator system is represented in this way. They have y of n minus n naught is equal to a sum over k, so k, and the sum over k starts at minus infinity and goes all the way up to n minus n naught. So let's go ahead and this is an example of a system. It goes all the way up to n minus n naught, and it's just a sum of x of k's. So it just takes x at whatever that k index value is. Now, before talking about this in detail, I want to point something out. And like this looks a lot like y of t minus t naught is equal to the integral from minus infinity to t minus t naught of x of tau d tau. So this system here is also the accumulator system. It's the 3111. It's the like linear systems version, and this is the discrete version. And the reason I bring that up is because we'll see this over and over again. And I want you guys to use that skill that you got in 3111 for analysis to understand linear systems. All right. So what?
I actually see it now. Now that you put it in the integral form, I see how the shift happens, because when you shift the index to the right.
Yeah, like so a lot of times this will get written differently. Is what I kind of want to point that out. A lot of times we write this down conveniently, minus infinity to t x of tau d tau, right? Normally you see this realization in class, right? It's the sort of simple form because we're not shifting the result back, right? This is saying, okay, I'm going to integrate to some, for some, in this particular case, we're considering some value n naught, right? And it's kind of part of the equation here. That's what makes this equation on the top different from the equation on the bottom. This says I'm going to integrate all the way from minus infinity up to time t, right? And so ultimately that ends up being the integral of x, right? And so this just ends up being the integral of x as well, but now instead of plugging in t as the operative variable, we're plugging t minus t naught as the variable, right? So say that you integrate the value t, right? What do you get? You got t squared over 2, right? And so in this case, if you integrate it, if x of t was this, y of t would be y of t squared over 2, right? If for this integral, instead of that, you would plug in it would be this, y of t minus t naught would be t minus t naught squared over 2, right? That's the answer to this question. Does that make sense?
Yep.
And so over here, we're doing sort of the same thing. We could write this out in the same way as y of n. It could just be the sum from k goes from minus infinity to n of x of k, right? And and ultimately for discrete systems, there are summation formulas that you use. So instead of using your integration skills, you'll use all of your power series and all of your geometric sum stuff in digital signal processing. So if we're going to analyze this system, that's the kind of stuff that you would do. But that's all that this is It's just integrating not up to the time n, it's integrating up to the time n minus n naught. Does that help?
Yeah, no, I totally see it now. When you put the integral, I realized what my issue was and everything.
Oh, okay. Yeah, I'm glad that I was able to.
The only thing that's kind of strange now, maybe I misunderstood the definition of time invariant, but it looks like this shift is equivalent when you shift the input and you get that shift in the output. So why is it not time invariant?
So the accumulator as a time invariant. So you're a little bit ahead of things, but I'll give you a technique for proving this. And I think it's the same thing that you get when you got 3111. But what you do is to prove that something is not time invariant, you basically put a signal through the system without a time shift, and then you shift the output, right? And so in this particular, so how would that prove? How do I? Oh, maybe I can go to the question slide. So you're getting a little bit ahead, and we'll cover this, but I don't want to. I mean, why not just give you an answer? I need something where there's blank space. Okay. So in doing a time invariance proof, so your question is really like, how do you show that this is not time invariant, right? Right?
Yep.
Okay.
Yes.
So the way that you do that is you do a time invariance proof, and so a time invariance proof works like this: you take x of n. All right, you put it through whatever system. In this case, this system is this infinite sum system, right? So you put it through, and then you get an output. We'll call it y1 of n, and then you delay the output by n naught. So then you delay, and you'll get y1 of n minus n naught. Okay, so then you go through another case, and you delay it first. So I'll put, this will be the delay system. All right, then what you put is the delay system first, delay, then you'll get coming out x of n minus n naught. Then you put x of n minus n naught into the system, h of n, and then you'll get an output, we'll call it y2 of n. Now, the idea of time invariance is that the output that you get does not matter what time that the input was applied. And in this block diagram, we take x of n and we apply it to the system immediately in the top branch. And in the bottom branch, we delay it, and then we apply it to the system. Now, the test for time invariance will ask, is the output when we do not delay it and when we delay it exactly the same signal? If it is time invariant. If it is not time invariant. So the accumulator system is integration. So the accumulator system is a time invariant system. Okay? Just because integration is both linear and time invariant. Okay? So when we do this, you'll find that, so let's go with the top branch. X of n goes in. All right, so so this is actually part of the analysis part. This is the actual integration system. This is when we do the time invariance analysis, what we look at. So this is our system, right? This is the first thing we have to do is accept like our representation for the system. This is the integrator system, right? The top branch, we do not delay it. So x of n goes in. So this right here, y1 of n, is actually the output of the integrator system. It is k equals minus infinity to n x of k. That is the output. That is y1. Then we delay it. y1 of n minus n naught. That gives you the equation that says k goes from minus infinity. Then we have to plug in everywhere where we had an n, we have to plug in n minus n naught. So that's why the top goes to n minus n naught. So that is the first, that's the top branch of our proof problem. Does that make sense?
Yeah, no, I totally see it now.
Okay, and now on the bottom, what we do is we delay x. So now at this point we have x of n minus n naught, and we put x of n minus n naught into the system. So that means that y2 of n is equal to the sum k goes from minus infinity to n of x of n minus n naught. And then you have to ask yourself, is this and this the exact same function? And in fact, sorry, this is k minus n naught. Right. And in fact, it is. Because when you go up to n, you get x of n minus n naught. When you go up to n minus n naught, you get x of n minus n naught. These are the two different ways of writing the same equation.
I see.
And that's how that is how the time invariance proof would be written in exhaustive detail. You're a little bit ahead, right? We haven't even talked, like, we're talking about the delta function and stuff like that, but that's what that proof is about.
So if they're the same though, then they're time invariant.
Yes, this is a time invariant system. Integration and summation are both time invariant.
Okay, I read at the end of this problem, it says this following problem illustrates that it's not time invariant. So on the next problem, and so I'm thinking,
this is a time invariant system.
Oh yeah, I see. I was getting messed up with the book. I think I read it wrong. It said the following, not this example.
Okay,
so
but the
really
book says this is time invariant, right? There's not an error in the book.
Yeah, it's time invariant. It's good.
Okay, good.
It's good.
Okay.
Yeah, thank you so much. Thank you so much. And I hate to take everyone's time. Just one last thing.
Oh yeah, that's all right. We're actually after class. I do have to transition to my office hours very shortly. But what's your other question?
No, yeah, it's just small. I have class at 2:30, so I can't make your office hours. So are you free ever Monday, Wednesdays, or Fridays in case I wanted to do something like an office hour?
Yeah, if you wanted to specifically talk to me, note that we also have a TA. So and we will fix our TA office hours on Tuesday. So you can make appointments with me, or you can meet with the TA. And so, of course, I can always make appointments for those that want to talk to me but may have a conflict.
Gotcha. All right. Thank you so much, Professor.
Yeah, thank you. And so that's a little technical, but that's kind of, this is a technical. We will be getting significantly more technical as time permits. So I don't know if there's anyone here. Is there any other questions? Well, actually, I need to transition to my office hour location. It's 2:30. So I will be in my office hours for those that would like to discuss more. And so I will talk to you all later. Goodbye. I have to save this. All right. We'll stop the recording.